So welcome to the Gemini Center on Quantum Technology. Today we have a talk in the quantum computing track. It's by Franz Luef. He's a professor at NTNU, and he will talk about novel methods for quantum information processing. So Franz, please take it ahead.
Okay, thanks. Thanks for inviting me to present in this venue. And I'm going to present some fairly recent stuff from a preprint from September, and then some older stuff. Why is it not? Yeah, okay. So the background is that, at least from a mathematical point of view, a lot of these traditional time frequency or signal analysis methods are have the same mathematical background as quantum mechanics or quantum information theory stuff. So many of these things are rooted in this Weil representation or Schrödinger representation of phase space, but of course the engineers think of it differently, so they want to analyze signals and so I was wondering some time ago if there's a way to do something that's more towards quantum than what has been done traditionally in signal analysis and time frequency analysis. And this is just a reminder that, I mean, you can always replace time frequency by phase space, as we will see. Very often it's necessary to actually go beyond Fourier methods, like where you have either time or frequency descriptions, and go for a setting where you have both time and frequency. Especially like in audio signals, it's very necessary that you know when and for how long your certain frequency content is present, and not just that it's there and only the amplitude, as in the Fourier transform. And here is some plots where you can see the signal, and then in order to make this work, engineers came up with the idea to localize the Fourier transform, so to use a window function that's compactly supported and decays nicely, and use this to localize your signal, and then do local Fourier transformations and do this over the whole signal. But this depends on the choice of this window, as we will see in a moment. And then you can also see it in the pictures. So depending on which kind of signals you have to analyze, you also need to pick your window accordingly. And there's also uncertainty principles coming in. So there's you cannot arbitrarily well localize in time and frequency, like you cannot arbitrarily localize your particles in phase space. And so it's a very subtle thing, like to pick the appropriate window function to analyze your signals in hand. So usually, if you have a certain class of signals where you know that they're not changing too rapidly or whatever, then you can pick your windows beforehand in a nice way, and then engineers know how to do this. But if you play around with this and do it, not in a clever way, then you will get very bad pictures and very, very poor information about your signal that you would like to understand better or transmit or analyze or change. I mean, these kind of methods appear, of course, in all this kind of audio engineering, if you want to remove noise, or if you want to make one part of an audio signal stronger than another, or select one part, or then you need these kind of tools to do this. And the main goal is going to show you that similar things can be done on the level of quantum states, or at least as a density operators. Good. So here are some formal definitions that we don't talk about this wake things. So I'm used to using what's called the short-term Fourier transform. So this G here is this window function that I talked about before. Usually something nicely compactly supported. Another popular choice is the Gaussian, because then you can compute a lot of things analytically, and it has also a nice link to complex analysis and tablets operators and this kind of things. But this is what I meant, like you take your function, you localize it with your G, and then you take a Fourier transform, and then you move your G further over the whole signal, and then you get a representation that covers both time and frequency content as at this time content, what kind of frequency content you have. And if you use the analog of this for the Weil-Heisenberg operators, where you then think of it in terms of positional momentum, but also disappeared in physics, in engineering. It's called in engineering empty ambiguity function. This is like a symmetrized version of this. It's just a change of variables. So then you get this symmetrized version, which I will call the ambiguity function. And they appear as matrix coefficients of certain representations, so the Schrödinger representation. So I'm used to using this time frequency shifted version where you have this e to the 2 pi I t omega gtx, and then there's this extra phase factor when you talk about Heisenberg-Weil operators in quantum mechanics. And then if you look at these inner products, at these VGFs and AFG, then you see it's just F against these pi of x omega g or against this rho of xp. Like the first phase-space representation or time frequency representation was introduced by Wigner when you look for this quasi-probability distributions. And it looks like this, and these two are related. They are Fourier pair. Also the Fourier transform of this is the ambiguity function. And there's a whole slew of time frequency representations, because this, for example, this Wigner things, Wigner distributions very often have ghost frequencies that you want to remove, and then you smoothen the whole thing by convolving it. And so if you do these things, for example, with the Gaussian, then it's called the Hosimi distribution. Exactly. If you look at this kind of pi of x omega g or this rho of x pg and take g the Gaussian, then you get coherent states. Good. So this is the background from time frequency analysis and then phase space description of quantum mechanics. And that's what we try to emulate now for more general operators. And also there's like versions of this in the finite settings where you do this shifts in this cyclic way, and you do modulations by square roots of unity. So there's like you can develop most of the stuff that I'm talking about also in this finite case. This is just a remark. I will not focus on this today. So one reason why this is popular is because it really, like in the Fourier transform case, allows you this information about this ambiguity function or the short-term Fourier transform at each point in phase space or time frequency plane to reconstruct any signal of finite energy, so any L2 function in this form, and it's like, okay, you take your time frequency count as information, this VGF, and then you weight your time frequency shift, this pi of x omega, we'll call time frequency shift, and integrate over the whole R2. And that's usually very often in physics called, when you do it for G the Gaussian, for coherent states. So this continuous resolution of the identity. and the advantage is now here that, for example, these building blocks here, they are all in L2. So if you start with an L2 function, since these are unitaries, you stay in L2. But on the other hand, you get like non-redundant over complete representations, which, yeah, so you want to like minimize this, how much you're over complete, and then you end up with looking for discretized versions of this. And in general, you can do it for general point set, but I will just state it here for lattices, like this rectangle lattice alpha set times beta set with density strictly less than 1, as alpha beta less than 1, and that take the Gaussian. And then it's not so easy theorem that you can reconstruct as before, but now with just points from this lattice. So your time frequency shifts from the lattice. And this is because these kind of system pi alpha k beta LG is what's called a frame. So it's like the way to fix this over completeness and redundancy and tame it and make it into some stable condition. So this is like you want to have some approximate Parseval type relation, and that's what the frame condition is giving you. And so it's then the non-trivial part is of course then trying to figure out if this constant A exists, this lower bound, and so for the case of the Gaussian, you use complex analysis to do this. And for each function that you're interested in, you have to do separately, and usually you need some extra tools. Function analysis is usually not good enough, so you need some extra stuff. But this is like this somehow can be thought as discretized coherent state representations. Good. So now let's see how one could do this, or how we propose to do this for operators. We propose the following and call it the operator SDFT. And if you see it for the first time, it might look a little bit strange, but it grew out of, hopefully we'll see why it's a sensible thing to do. So we do S star pi of Z star T. So we want to analyze T with respect to now an operator window S, and we sandwich this in between this pi of Z star. And of course, you can also do the rho, but most of my papers so far have been with the time frequency shift, so I keep it this way. And so maybe we should do this example first. If you do this for so you pick so how to get back the original thing that we know of. So how do we get back the SDFT of a function with respect to a window? And this was noted by Eirik Skrettingland, one of my former PhD students. He said, "Oh, let's use some auxiliary vector E, some unit vector in L2, and look at this rank 1 operator F tensor E and G tensor E, and if you compute this, and so somehow that's how he set up the definition, that you get like a scalar multiple of this rank 1 operator, and therefore somehow we now can associate this rank 1 operator to our weighted with our VGF. And if you do this for finite rank or for arbitrary, if you are careful enough, then you can end up with like all these SDFTs of the data points you're interested in with respect to some windows that some different windows. So this, for example, is and it also keeps track of like so usually if you do this in applications, you do all these SDFTs, and then you don't know how to store them, but now thanks to this relation here, we have this, that at each EI tensor EJ, this somehow matrix unit, you put your VGI FJ, and so if you, for example, do this for time series data, you actually get like an ordered, it's a time ordered change of your spectral behavior. You can actually see it, how the spectral content changes in the time frequency sense. And so this is, and of course you can use the same G and F, and of course, and the other way of thinking about this is like you look at this rank 1 operator, this E tensor E, and you take a square root and analyze it. And the same, more general with the S and T's here, if you take some nice positive operators, then you take the square roots and do and assume that they're compact or something, then that you have some nice decompositions like this, then you always end up with this kind of description. And this turned out to be very useful. So we used it for some problems in machine learning, and so recently my student Erling Svela and Daniel Abreu and Michael Speckbacher used it for establishing some Donohue-Logan sieve inequalities that are useful for, that originally were used for compressed sensing questions. So, and it turned out that because it's a linear thing, as in T, and conjugate linear in S, it preserves, so you can do a lot of things that you, with other time frequency representations for operators, cannot do, because usually they are quadratic. And the nice thing is it behaves exactly as it should. Like if you know the relations for the one for functions, BGF, then you will see it captures all the, it has the same properties. In particular, it has this thing here, what's called Moyar's identity, or the squared equality of this representation. And in particular, if you pick Q equals S and T equals R, then you get this condition here, which somehow, if you normalize your S to have Hilbert-Schmidt norm 1, gives you that this mapping that sends T to VST is an isometry, and this gives you then automatic, as a consequence, this reconstruction formula. So we can reconstruct now an operator using this operator SDFT, and instead of the function that we had before, this time frequency shifted to function, we have this time frequency shifted version of the operator where the order is not different. It's S star pi of Z. And yeah, so that's like the non-standard thing, but in the rank 1 case, it really reduces to the thing that you have seen before, and in the other cases, it really gives you some nice way of reconstructing your T from this SDFT for operators, and yeah, and so before I said, okay, we have some kind of a frame condition when we want to discretize this. So the same thing is here. We want to discretize this now. We want to find somehow a way to discretize this. And there, luckily, already existed a theory that we could apply to this. So these kind of systems that we look at, or we're not sure, ended up looking at, have been introduced in a much more general setting by Wen Chang-sun in the 90s or early 2000s, where he introduced the general notion of frames, where he replaced this inner product things that we had before. So where it's actually saying you project onto a line, onto this line spanned by G naught. You just can take any subspace you want, some nice closed subspace, VI, and you take a whole family and you just model this. Then you just replace the previous condition by the appropriate analog for the subspaces, and that's what you call the G-frames, and everything works as it should. And you can, I mean, implicitly, I didn't really say it, but the key thing is like you want to, in order to get this reconstruction formulas, you study this frame operator, and you can do this here and behaves nicely as it should. And in our case, these SIs are coming from like S pi of lambda, as a S star pi of lambda star in that. So these are like our analogs of this generalized operators and in generalized frames, and we do it for operators. So we start with a nice operator, and then we look at this composition of time frequency shifts, and that's our building blocks. And if you do this, then you end up with the following version of a G-frame for operators or states, which looks like this. And this was first done by Skrettingland in a paper some years ago, and we now realized that it fits very well with this operator as Tifty did it before. And if you have this relation, then, for example, this forces S to be a Hilbert-Schmidt operator, and it also allows you to get this reconstruction formulas as before, but now discretized. What else can I want to mention? So, in order to make this work, something similar like in the classical case, you have to restrict to some nice class of operators before you have to restrict to a nice class of functions. And for functions, it turned out that Feichtinger's algebra is the right way to do it. And the analog here is what we call Feichtinger operators. And it's like you take the SDFT with respect to some nice S trace operators, or even like we usually take for computation the one associated to the Gaussian, so the rank 1 operator associated to the Gaussian, and then you force it to be an L1 function. So this SDFT here is of course operator valued, so it actually Hilbert-Schmidt valued, and if you take T and S in T and S not Hilbert-Schmidt, then and then you force it to be and like have some L1 integrability, and this can be thought as like an analog of test functions, and this is like the Banach space version of what Kyle, Keukas, and Werners call Schwarz operators, which are the analog of Schwarz functions. And there is, of course, the analog of on the distribution side for those who know about this. Good. So then, what did we do with this? So we actually introduced, I mean, this L1 condition can be relaxed to some more general mixed LPQ conditions. And if you do this, then you end up what's called modulation spaces or co-orbit spaces. And we introduced the operator analog of this. And independently at the same time, Peter Ballach and Lukas Kohltorfer from Vienna also introduced operator co-orbit spaces, but using a very different approach. And together with Lukas, we were able to show that this is exactly, that these two descriptions are equivalent and describe the same classes of operators, and that you can use this to actually introduce a notion of sparsity, and that this G-frame condition as a expansion that I wrote down actually can be has this compressed sensing type structure that you take the n largest coefficients, so you take the Hilbert-Schmidt norm of these coefficients, and then you end up with, then you can show that you can actually represent your original object with just finely many well-concentrated coefficients. So you can actually implement this, and this is what Monika did, and she actually did experiments where it shows that if you do finite rank operators instead of like rank 1, which would correspond to the classical function case, that you actually get better sparsity results. So better, you need fewer coefficients, and it's better concentrated around a few coefficients than the traditional way of doing it. Okay. So the thing that we used, I don't know, I just mentioned it briefly. If you write out this expansion, you end up with using what's called the translation of operators, where you conjugate your operator by your Schrödinger representation, and what we also what we use a lot in our calculations is that there is a way of convolving two trace operators and then a one function, a trace course operator in this way. So maybe this one is like, this is like creating a mixture of rank one or a noisy version, a smeared version of your original S, and then you weight it. So this is really analog of like this type of filters that you see in time transition current settings. And this is like if you take the standard definition of a convolution and replace everything by operators, where you replace your translate by this, by alpha z, and your integral by trace, and your flipping by conjugating with the flip. And it turns out that in the rank one case, you get back the traditional results, as not traditional notions that we saw before. For example, the modulus squared of this STFT is the spectrogram images that I showed you before corresponds to this rank one convolution of operators. And like cutting out certain things from a signal corresponds to what's called localization operators, and that's again the rank one version of what we have seen before. And most of the stuff that you want to do in harmonic analysis you can do, and this was shown by Vianer in '84. You can do Young's inequality. You can do you can also do Fourier transforms, which is very often called the characteristic function in quantum mechanics. And there's a way of turning these convolutions into products. There's also a way of like expanding your S with respect to this, as it is a Fourier transform description of your operator. And there's also Hausdorff-Young and so on. So, but I think I'm running out of time. So these kind of tools we use to actually establish this kind of results about this operator STFT or other stuff. I think if I have more time, I can of course go on, but I can stop here.
Well, thank you very much for the nice presentation. Are there any questions or comments? Don't be shy. If not, then thank you very much.
Can I ask something? So, Franz, you say that some of those finite rank choices are better than just rank one. Do you somehow tailor them to the operators you want to the S or to the T, or is this...
No. It actually, if you,
is there some universal choice? I mean, no. Is there some?
No, there's no universal choice. That's the same problem as before. But using more functions to do it as of that have like different characteristics than just one function allows you to pick up different things. I don't know. We just started doing this in September, so like this year, and so far, of course, it's just a proof of concept. But at least, mathematically, we can at least show that we have this best n-term approximation, this matching pursuit algorithms like Donahoe and these people had for compressed sensing. So you, for example, can now also go on and do this restricted asymmetry property and all this kind of things that have been done for signals and wavelets and stuff like this. So the same machinery works here as well.
Thank you.
Any more questions, comments? If not, then thank you very much one more time.